Oh, no.
Introduction that matters. That is gone now. No, I don't want it. Okay. So anyway, I will just continue with the outline. So the next stage would be to address the SIM-TFTs, the way they appear in the context of geometric engineering with isolated singularities, and then advance that to the level of so-called nested SIM-TFTs associated with non-isolated singularity examples. Then in the last part, which is sort of the key technical part of the work that I want to highlight, is the study of anomaly terms in SIM-TFT directly in singular geometries, okay? And consequently, the actual computation of such anomaly coefficients. Both solid results for isolated singularities and empirical results for non-isolated singularity examples. Okay? And then I'll conclude with some minor outlook and concluding remarks. So the focus specifically here will be for specificity, M theory on non-compact singular space, that we will choose to be non-compact conical Calabi-Yau threefold. And the prototypes that I'll highlight would be non-compact orbifolds with the finite group gamma sitting in SU3 holonomy, the resulting quantum field theory via this geometric engineering is consequently quantum field theories in 5 dimensions that has supersymmetry. So let me just highlight first the notion of higher global symmetries in quantum field theories first. They are obtained by introducing non-dynamic extended defects in the resulting quantum field theory and the corresponding symmetry operators that act on them. So one-form symmetries are associated with, for example, with string defects and the corresponding dual operators acting on them. Similarly, of course, our well-known zero-form symmetry is associated with the point defect and corresponding symmetry acting on it. There are examples in quantum field theory where actually one-form and zero-form symmetries are intertwined. They are non-trivially connected, which leads to the so-called two-group structure symmetries. Now, how about higher symmetries in string theory, geometric engineering? So I want to claim this is very natural. So we have a target space associated with symmetry defects, like strings and corresponding operators. And in string theory, what we have to add is to this target space the non-compact singular space. So the prototype examples of isolated singularities would be construction on a conical non-compact space, where at the tip of the cone, the singularity signifies the appearance of quantum field theory in the dual space. So the symmetry defects in the target space are, of course, non-dynamic. There are non-dynamic extended defects that then in the extra dimensions of this non-compact conical space wrap additional non-compact cycles. Furthermore, the corresponding operators that act on these defects are in the additional space associated now with the operators that are associated with branes wrapping now only cycles on the boundary. So this geometric observation, as I said, defects that wrap non-compact cycles, and symmetry operators wrap cycles on the boundary in the extra space. This geometric realization of a higher symmetry defects and operators, okay, has more of a recent history. And for the example, say, of M theory, is associated with M2 branes or M5 branes, wrapping for the defects, this non-compact cycles that are quantified. The defect group is quantified by relative homologies of that type. Okay? And the corresponding operators are quantified by the homology that specifies cycles on the boundary. We were primarily focused on examples of electric defects and associated with one-form symmetry. Okay. Now, how about introduction of symmetry theories in the context that I'm talking about? So in quantum field theory, okay, the introduction of symmetry theories is initiating by trying to study these higher symmetry structures and how they are represented in this quantum field theory. In particular, what we want to study, whether the symmetries are spontaneously broken or not, how they introduce constraints on the spectrum, representations, can we calculate the associated anomalies in this context? Okay. So to address those issues, we basically start with quantum field theory in, say, d dimensions, and isolate the symmetry structures that we are after into topological field theory in one dimension higher. And this is what we refer to symmetry topological field theory, or SIM-TFT, in one dimension higher. So in particular, we start with quantum field theory in certain space-time dimensions, and now we augment this to SIM-TFT in one dimension higher. Where on one side, we are dealing with physical boundary conditions of the original quantum field theory. On the other edge, we are dealing with boundary conditions that are topological and crucial for describing the full SIM-TFT structure. So it turns out for many questions we want to ask actually is this boundary conditions and this TFT itself that are crucial for the analysis. In any case, we want to implement that now within geometric engineering, and the claim is, again, this is very natural. Introduction of SIM-TFT in geometric engineering is natural in the sense that, say, this example that I highlighted for defects and symmetry operators on conical non-compact space with isolated singularity, okay? We obtain the additional direction of SIM-TFT precisely from this radial conical direction. So compactifying this additional space on the boundary over these radial slices produces precisely the extra direction that specifies the features of SIM-TFT in one direction higher. And again, here at this, on this side, we are dealing with physical boundary conditions. Here, at the technical infinity of the radial slices, we are dealing with topological boundary conditions. Okay. So physical boundary conditions, again, come from the singularity structure. Okay. Topological boundary conditions we typically obtain in this case from 11-dimensional supergravity boundary conditions when compactified on these boundaries over radial slices. Right. Okay. Now let's generalize that. Okay. So I want to highlight generalizations of quantum field theories and their SIM-TFTs to so-called nested SIM-TFTs. the prototype example in quantum field theory of that type would be to start with quantum field theory in, say, d dimensions, and we insert into this quantum field theory a defect quantum field theory in lower dimension. And the question you want to ask for such more complex quantum field theory framework, what is the symmetry theory of this combined system? So we can envision that as starting with capital D dimensional field theory, inserting here defect quantum field theory in lower dimension, and building SIM-TFTs above that. Okay. Now the easiest way is to actually start with this big quantum field theory and KK reduce it only to have one dimension higher than the defect field theory. And so this produces for us basically this line of this high KK reduced higher dimensional quantum field theory. On this edge here, we have a defect field theory. And now we build the corresponding SIM-TFTs. So naturally, from this defect field theory, we are dealing with this boundary SIM-TFT, one dimension higher. And above the higher dimensional field theory, we build this bulk SIM-TFT. Okay. So we see that the defect physical boundary conditions, right, are sort of at the corner of this physical boundary condition of higher dimensional field theory and the edge SIM-TFT of the original set theory. And now what we see is there's this interplay between the bulk SIM-TFT of bigger dimensional field theory and the edge SIM-TFT. And the corresponding boundary conditions now that we have to properly include in this context. Okay, so this is the field theory example of what we refer to as nested SIM-TFTs. So how is that realized in geometric engineering? Okay. So the statement is that nested SIM-TFTs of that type in geometric engineering, of course, are natural, and they are associated with non-isolated nested singularities. In particular, what the original SIM-TFT with isolated singularities is, what SIM-TFTs are to isolated singularities, nested SIM-TFTs are to non-isolated singularities. And that was realized rather recently from that perspective, and shortly after that followed up by a number of groups. Okay, so let's talk about the geometric engineering prototype of nested SIM-TFT. Again, our favorite conical orbifold as a cone over S5 mod gamma, where finite gamma is within SU3 holonomy. And within this construction, now we are also having flavor brains, singularities associated with codimension 4 loci, which are again cones of S3 mod some discrete action. Okay? So in addition to isolated singularities, we are having sectors where we are dealing now with extended singularities that are in real codimension 4. Okay? So prototype. Our favorite prototype is Z2N orbifold with this action on each of the complex planes, 1, 1 to n minus 2. And in the sector n, we are dealing with codimension 4 loci that appear there, that extend all the way to the boundary. So those are these flavor brains, right, with the associated with the C2 mod Z2 action perpendicular to this codimension 4. And there are two ways of describing geometry of this orbifold. One is the cone, our favorite one, singularity the tip, and then flavor extended codimension 4 singularity, or viewing it as a particular vibration over the third coordinate. Okay. And the symmetries, especially the action of discrete finite parts of this group of the orbifold play a crucial role in identifying subsequent SIM-TFT features. In any case, What we are describing with this Z2N orbifold is at the tip of the cone, we are dealing with isolated singularity, SUN, resulting 5-dimensional, actually SCFD. And now, on top of it, we are having sector where we are having now flavor brane, which are could dimension 4 singularities extended up to the infinity. And this is perfect prototype of nested quantum field theory. Namely, what we have is we have lower dimensional SUN, 5-dimensional SCFT, as a defect that is now nested into 7-dimensional SU2 super Young-Mills theory associated with this non-compact cycle wrapped by flavor branes and forming this bigger quantum field theory. So that's precisely an example of this defect inside the bigger field theory. Okay, so there's natural notion now to build out of that the corresponding SymTFT. Okay. 5D is here at the tip, yeah. Sorry? Could you speak up? It is, well, it is precisely specified through the symmetry structure. Okay, so in this vibration, you see this is, you have at codimension phi, the singularity. This is the vibration with this fiber degenerating the C2 or Z2N. The whole thing is, yeah, I think I'm showing geometrically precisely what's happening in the geometry. So, so if you're concerned about the action of discrete symmetry terms, this is specified in the geometry of this codimension codimension 6 singularity. Yes, you can do more. Yeah, you're thinking also the quiver, right? Picture as well, and so on. Yeah, yes, you can specify that more precisely, but I don't want to go into it right now. I'm focusing on just one specific thing, which are higher symmetries, which are torsional, is discrete finite group structure that I want to focus. The rest, the old story, yeah, is quite well understood. In any case, so so this example was our favorite example really quite a while ago, right? Where we went directly into this orbifold construction of that type and identify geometric origin of this higher form symmetry, in particular at the defect level, okay? Both 0 form, 1 form, and the non-trivial intertwining that happened and produced two-group structure. Okay? So what we did there, we used algebraic topology. What we did is we cut and glue singularities only on the boundary of this non-compact space and employ the so-called Meyer-Vietoris exact sequences to extract the dimension of the defects groups, both for 1 form, 0 form, and their intertwining structure. So that was without SymTFT. Okay. Last year, what we did is we advanced that to construct it actually the structure of nested SymTFT in this the system itself, so augmenting it by this additional direction. And so viewing that as a joint D7, quantum field theory system, constructed this nested SymTFT, and of course reproduce results directly by looking at the defect groups. But we see more structure. We have also more detailed information about the structure now. In particular, we see how this topological operators behave and are constrained due to symmetry, bulk, TFT being constrained by the boundary SymTFT associated with the defect group. So how the spectrum is specifically constrained just from the physical boundary conditions in this nested SymTFT. So how am I doing with time? Not so good. Half an hour? Okay, so let me, so then I'll just mention that, because how this construction of nested CMTFT now technically works in this context is starting with this combined 7D, 5D as system, right? And then what we do for this extended flavor brane that correspond to 7D's super Young-Mills theory, we compactify along the circular direction to get just 6D Kaluza-Klein reduced field theory. And at the edge here, we are dealing with resulting 5D SCFT, right? So this is the field theory picture. Now, how do we construct SIM-TFTs in this context? Okay. So what we have to do is we have to now describe normal geometry both to the flavor brane in this orbifold and, of course, the corresponding codimension 6 singularity, normal geometry there, okay? And obtaining now via reduction in this normal geometry along the radial shells, the resulting 6-dimensional SIM-TFT, that would be the standard one that we would have had just with isolated singularity, but now we are producing also over the flavor brane, the 1-dimension higher SIM-TFT. And now this edge SIM-TFT of defect theory, okay, imposes boundary conditions on this bulk SIM-TFT of the flavor SIM itself. And we can actually study that at the level of constraining the spectrum of the theory. And I'm specifically focusing on one-form symmetries here. Yeah, so I said those things. Now we have to. So how does this nested SIM-TFT that we constructed in this context constrains the spectrum? Okay. In particular, I'm going to focus on one-form symmetry example. Okay, not the whole gauge theory and all that. One-form guys, which are associated, which are obtained actually as 2 cycles B2 fields that sit in the bulk symmetry. That comes from taking 3-form M theory, 3-form potential, and reducing it on S3 mod Z2. This is the flavor part, okay? And then similarly, we are dealing also with one-form symmetry fields associated with co-cycles that are associated with the edge field theory, which which possess Z2N symmetry. So this is that will be just if we had only isolated singlet, now we have the effects also of the bulk associated with the flavor. Okay, and now bulk and flavor, bulk and edge of SIM-TFT interact. So we have boundary conditions on the right edge that force this bulk one-form symmetry fields to be subject to these boundary conditions. So we don't have the whole set of 2N, 2ZN, okay, one-form fields in the defect field theory, but these boundary conditions really fix N of them. So the resulting thing of this boundary interface, boundary conditions, is that resulting one-form symmetry is not Z to N. That's maybe one thing that you might have been interested in, but is now reduced just to ZN symmetry. So it's this interaction piece, and the ZN symmetry is really the coset of the flavor, modding out by the flavor discrete symmetry and the original whole gamma of the orbifold that specifies isolated singularity, one-form symmetry. Anyway, this is, and one can study geometrically how this happens, lots of interesting things. But I want to jump now to the recent things, okay? More refined calculations in geometric engineering. In particular, determining the actual coefficients associated with anomaly terms. Okay? So this is now the second part of my talk. Oh, well, this is just highlighting this interface. It also has between bulk and boundary. See if it has to do with appearance also. Sorry, that's a side thing. Let's go to the to the main part, second part of my talk, which is really now using the SIM-TFTs in geometric engineering to obtain coefficients in front of anomaly terms in these constructions. Okay? So, reminder again, we are dealing with M theory on in, say, d plus 1 dimension, small d plus 5 dimension in our case, and the extra non-compact space is a cone associated with 3 dimensions, special holonomy space. In any case, if we are dealing just with isolated singularities of these cones, if we excise the tip of this cone, topologically what we are dealing is now with a resulting space-time, in our case in 5 space-time dimensions, the boundary, and now this interval, radial interval that I was highlighting. And again, just reminder, SymTFT is associated with resulting quantum field theory in 5 dimensions and this extra interval that follows from compactifications on the boundary. In any case, so it's this SymTFT that I want to highlight, okay? And so I want to get now particular terms in the SymTFT, okay, whose anomaly coefficients I want to calculate. Okay? So starting point is the whole theory is in 11 dimensions. We are dealing with 11-dimensional supergravity, and of course I'm going to focus on the famous topological terms that is associated with the 3-forum gauge potentials, its field strength, and of course it has the geometric part associated with 8-forum characteristic class that we represent in terms of Porte-Eigenclasses classes of the tangent 11-dimensional space. So this is the original topological term. Because C3 is not globally defined, we like to represent this 11-dimensional action in terms now of 12-dimensional one, okay, that is globally defined just in terms of a 4-forum field strength and the geometric parts, and is often referred to as Chern-Simons action in 12 dimensions. This is the starting point. We want to embed that into our resulting SymTFT. Okay? So what we do is, okay, oops. Oh, that's not a crisis. Okay, okay, good. So, what we want to do is we want to rewrite this Chern-Simons action, which is our anomaly action, by splitting the 12-dimensional space into resulting quantum field theory cross interval SymTFT and the extra non-compact space. Now, this extra non-compact space definitely has to have the same boundary as the original singular space. But in principle, because of the topological nature of this coupling, we can modify, deform this extra dimensional space into one nearby, regular, as long as the boundary is the same. So this is our starting point to calculate, to determine anomaly couplings. It's from this type of action, okay? So let's see what we are doing. I'm focusing on 1-forum symmetry. My extra space will be with isolated singularity. Again, my favorite conical orbifold. Symmetries, as I already highlighted, associated with 1-forum symmetry are distortional B2 fields that actually enter the expansion of the field strength. So there is the resulting 1-forum field, and then we have the field strength that lives now in the extra non-compact space and is associated with particular second cohomology in this extra space. Okay. So expanding now the original 11-dimensional action, this anomaly 1 now over the X prime, right? F2s that now sit in the extra-dimensional space results in this 5-dimensional action, okay? So we have this B wedge F type terms that happen to have coefficients you can calculate precisely related to the order of the discrete group that specifies orbital. And then we have self-anomaly term that involves 3 B2 terms. Is the self-anomaly terms whose coefficient is geometrically represented as integral of the field strength that lives in second cohomology in the extra non-compact space and extra geometric parts itself. So calculating this quantity will give us the actual anomaly coefficient in the resulting SIM-TFT. Okay? So this is the goal. Okay, so the goal is that, and that is sort of rather obvious, but it was also studied by the group prior to. In any case, so how are we going to calculate that? Okay, I want to calculate that directly in singular geometry. I don't want to go to resolution and all that. Okay, and the trick that we are going to use is employing the index of Dirac operator on this extra space that is coupled now to a line bundle that is governed by the first term class of this field strength. This is the famous Atiyah-Patodi-Singer index that is associated with this type of Dirac operator. So this index has two parts. The bulk part of this extra space that has now this first term class and Pontryagin class. This is the bulk part, and it has the boundary. And the boundary is built out of two terms. One is the so-called kernel of the Dirac operator, the boundary, which in our case is 0, and the spectral invariance of the Dirac operator on the boundary, the so-called Eta invariants. So bulk term, boundary term is equal to the index that is integer. Now, if we look at this bulk term and replace first term class precisely with the field strength F2, this is precisely the anomaly coefficient. Okay? And the second part is just the boundary part, which is only this Eta invariant. And this is index. Index is integer. Boundary of deformed or region singular space is by construction the same. And we get direct formula for the calculation of anomaly coefficient modulo integers in terms of Eta invariant. So this is the key result, that anomaly coefficient can be calculated directly from the boundary of the singular space, if we know how to calculate this. Okay, so this is another, well, it's beautiful thanks to math people, right? We are importing those things from the math community, okay? And it so happens that for orbifolds with isolated singularities that I was highlighting, so with the weights in each of the planes, P, Q, R, okay, and this boundary, we can get the Eta invariance precisely calculated. At the end, this is really work of Baer when applied to this case. And it has this beautiful form in terms of the phase associated with Z and orbifold, weights of these phases by P, Q, and R, and summing over all the sectors. Right? So this to me, I love beautiful formulae, and this one is really wonderful looking to me. So in any case, this is, again, mathematicians have done that for us. Okay, so let's see, where are we the status of anomaly coefficient calculations for isolated singular? Old story. What we do, we resolve space, employ techniques of algebraic geometry, intersection theory, and apply directly to calculation of these bulk terms, which is alpha directly. And this is the old story. Okay? New story. We do only the singular space and get the results from the APS index that the same anomaly is associated precisely with the Eta invariance on the boundary. No resolution. If somebody calculates that for me, I have an anomaly. Right? And so, for example, of particular Z and orbifold, this one, This is isolated singular orbital. It so happens that, yeah, this has been calculated by this technique, and you get an answer. This is calculated applying Bayes' result and get this answer. And of course, they agree. Okay? And then we looked at ZPQR, we resolved them, did calculation here, applying Bayes to all ZPQR, ZN PQRs with isolated and got complete agreement. So this is sort of neat thing, and to bring it to the community, right? We can do that. Okay. But the real prices for non-isolated, those that extend, flavor brains extend to the boundary. Okay. And there our story is still under development. Okay. So in the last few minutes, okay, let me highlight that part. Okay. Again, those are now non-isolated singular, my favorite example, that was the Z2N orbifold, okay, with flavor brain extending to the boundary, D7, D5 system. And we identified one form symmetry already, carefully. Now, the anomaly coefficient. Now we cannot use directly the techniques to calculate eta invariant, the boundary eta, because the space is singular on the boundary as well. Okay, because this extended singularities go to the boundary. Okay, but let me point out what has been done so far. Okay, it so happens that this group was studying examples of YPQ cones, strictly isolated, but they went to some limit that happened to coincide with the limit of this orbifold with non-compact signal, and that's the result. Okay, they got this result. This is all resolution, right? Old story. Another coincidence is that actually this Buko et al. Calculated this anomaly for this orbifold directly in field theory. They knew the spectrum, one loop, they did the calculation. Just happened this example to be in the literature, okay? And of course, these two results agree. Field theory should agree with what geometric engineering does via resolution. Okay. Now comes our approach via singular spaces and eta invariances on the boundary. Okay. And so we have the following empirical answer for anomaly. It has the standard, not so standard. It has the eta invariance associated with this boundary itself, but it excludes this eta invariance, this special invariance calculated by the Garatu that excludes the sector where we have this fixed flavor brain, right? Natural, you would assume that. And that was done for this invariance, calculated, and that's the answer, beautiful, excludes the sector, okay, of fixed flavor brain. What to do with the fixed flavor brain? This is nothing extended to the boundary. This is very hard to calculate. We don't know how to calculate it directly. Naive argument would be that that would be associated with some S3 eta invariance because those are 2-dimension 4 loci, right? Where the discrete group might have been this flavor Z2 group. That would be more naive statement because that's what flavor brains do. The answer is no. The answer is it's eta invariance of S3 mod the coset group, which is precisely one form symmetry that I was already highlighting. You know, Z2N, mod ZN, Z2 is ZN. This is the resulting. It happens, it's not geometrically completely intuitive. We don't know where it comes from, but this is the answer that we had. And it turns out to, this is the answer. We get this calculation and turns out to. So this is our empirical understanding of what. We found a bunch of classes of examples of orbifolds with very similar structure. That, namely, one form symmetry is associated with original ZN order of the orbifold, modified out by the flavor order symmetry. Okay? Those are one form symmetries. Okay, and in this particular, all these particular examples, you see there's certain relative weights, right? We got precisely the sense. It works. Because what we did, we resolved all that for all this example, got alpha. Now we have directly a calculation with eta invariance, and is this S3 correction that is modded out by the one-form symmetry action. Not all examples work like that because you can have more complicated ways, but these classes all fall into this and agrees with explicit intersection calculations for all this example. So this clearly is is bringing up the issue. We have to understand it better, possible generalization, and first principle calculation of this eta invariance coefficients. We tried, we compactified, we tried to cut out things, very hard. But just want to point out this is where we are, as I believe state-of-the-art things. Okay? So let me conclude. Right. So I tried to give you a bit of an overview of the status of calculations of properties of quantum field theory in geometric engineering, in particular focusing on how far we advance this work with non-isolated singularities directly in geometric engineering. And now I'm also highlighting some of the aspects of more refined data, which is eta invariance and anomaly coefficients. Having this more refined information about anomaly coefficients would also could point to us also, but in what manner, more specifically, we are breaking these anomalies when we compactify space, because these are anomalies, they cannot be there, they have to be broken. And how to quantify in this gluing procedure by what states do the breaking in what amount. So there's clearly opening the directions for more refined work. We've done more hands-on Meyer-Viatori's things, understanding sort of the group elements of different terms in these compact spaces, but this opens the door for more refined understanding of that, okay? Clearly, isolated singularities, frozen singularities, this is the only thing that we could have in this context. So this is the only thing we can apply to. Terminal singular, again, this is something that could be potentially applied. But one thing that is sort of intriguing to me is actually generalization, well, non-toric, non-abelian, right? Examples of nested singularities, but non-supersymmetric constructions. Atiyah-Patodi-Singer theorem does not rely on additional space to be supersymmetric. There's nothing about special holonomy in these additional spaces. So calculations of that type should be directly applicable to non-supersymmetric orbifolds, at least with isolated singularities. You see that really as a one step only in this context. And luckily, the mathematicians have already addressed some of the examples of just R6 mod something, or because we are non-supersymmetric, and anomaly coefficients, I think, with their techniques can be now directly applied to this example. No supersymmetry needed. It's really just the issue of isolated singularity and eta invariance at the boundary of the spaces. So I think that's personally quite exciting that we can apply that directly. But I think that the ultimate prize, these nasty things would be really beautiful to quantify further, as I was highlighting at the end of my talk. Thank you.